Okay, so we're recording. This is Sunday, February 16th with the Upstate New York math team, and we're going to have a math talk about the number 2025. Let's see if I can get this started. Here it is. So welcome. We're just getting started with a math talk about the number 2025. Um, we are recording this to the cloud, so I'll be able to share the notes afterwards. So the answer is 2025. And here's the question. How many small squares are on the next slide? If you'd like to guess the answer, you can type that into the chat or unmute and give the answer. Okay, we have a correct answer so far. Here's the picture. There are exactly 2025 little squares on this screen. And it may help if I add some guidelines. It's really a 45 by 45 grid. There's 40, there's 40. And if you multiply those out, you'll get 2025. It's actually easier if you do move the bottom over, and so that you get a 40 by 50 rectangle with 25 dangling there off the bottom. And this brings me to one topic I'm going to use a lot today. It's called the area model for multiplication. And this is something I actually use in my developmental classes, but it's a really good analogy for multiplication, partly because area satisfies the commutative rule, um, and it also satisfies the distributive rule. So it follows the rules of arithmetic. And so we could even draw a bad drawing, not to scale, but we have a 45 by 45 square, and we're moving the yellow rectangle from the bottom over to the side, and we end up with um, the 45 squared is actually 40 by 50. You have to look for the 40 by 50 rectangle and then 25 more. Um, and so that 40 times 50, that's really four times the next number, four times five. There's 100, and that doesn't interact with the 25. And so we get four times five is 20 and a 25. And here's the audience participation part, some mental arithmetic practice. So feel free to type your answers into the chat, or you could unmute and shout it out. So first, what's 5 times 5? Well, just a quick warm up. Okay, good. I see a 25. What about 15 times 15? Okay, good. We're getting some answers. It's 225. Notice it's that one. 1 times the next number is 2, followed by 25, 225. What about 25 by, uh, what about 25 times 25? Okay. Oh, we're getting a lot of good answers. So notice it's the 2. 2 times the next number, 3 is 6, and followed by 25. Moving on, 35 by 35. Yeah, it's going to be tw 1,225. The 12 is from 3 times 4, and then we have a 5 squared. Moving on, 45 squared. Well, we did that, so we'll just put in the answer 2025. This is some fun mental arithmetic. Um, 55 squared. Let's make it quick. 55, 30, 3,025. That's right. 5 times 6 is 30, followed by 25. 65 squared. Okay, I think you guys are having this ready to go. That's right, it's 4,225. 75 squared? Yeah, I'm seeing the answers coming in real quick on the chat. 5,625. 85 squared? Yeah, that's a 7,225. The 72 is just 8 times 9. And finally, 95 squared? Yeah, it's 9,025. And I love that this year, 2025, is part of that pattern. It's a way you can square some numbers really quickly just mentally. Let's go on to the next problem. What's the sum 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9? Okay, a lot of you know it. Um, I'm going to use the area model. So I have these thin rectangles, width 1, height 1, 2, up to 9. And the trick is that we just double it and we end up with a rectangle. There's 9 across and 10 over. You've probably seen the arithmetic way where you just reverse the sum and then add downwards to get 9 tens. So you're getting 9 times 10 over 2 or 45. But let's get a harder one. Um, in a 9 by 9 multiplication table, what's the sum of the numbers on the inside? And here it is. Here's your 9 by 9 multiplication table. You may remember this from fifth grade or first grade. Um, okay, the answer is 2025. That was sharp. Um, so this picture is not to scale, but I want to look at this as the area model. And in the area model, if I draw it to scale, it actually looks like this. Do you see that if you zoom in, look really carefully along the top, there's one square followed by two squares, then three squares. So the length is actually 1 plus 2 all the way up to 9. And every grid there is an answer to a multiplication problem. So to add up all of the numbers in the multiplication table, we're really looking for the sum of the areas in this picture, which is how many small little squares there are. And the answer is 2025. It's a square. It's 1 plus 2 plus all the way up to 9 squared, which is 2025. Nicely done. There's a picture that I want to show you using the same 45 by 45 grid. And if we divide it into these L shapes, um, geometrically they're called gnomons with a G, gnomons. And there's something really special about it that every gnomon can be filled up with squares like this. Like that last one next to the 9, it actually has 9 squares. Each one is 9 squared. The one with sevens, there's 7 squares. Each one is 7 by 7, and so on. Even the even ones, the 8 one, there's 7 squares. Each of them is 8 by 8. But then there's 2 half squares that make an eighth 8 by 8 square. So if you look carefully, you should see that at the very beginning, we have 1 cubed. The next one, we have 2 cubed. There's three squares, that's 3 cubed. And so on. So we're really looking at the sum of the first 9 cubes. Do you see that in this picture? That's the sum of the first 9 cubes. And that means that the sum of the first 9 cubes is actually the square of the sum of the first 9 numbers. And that's 2025. So the answer is 2025. Um, let's do some more number theory. Um, what are the I want to talk about the factors of 2025 and their sum. And one thing that I was taught when I was a kid was to make a factor tree like this. You can factor 2025 any way you want. I happen to write it as 15 times 135. Each of those factors further until you get to prime numbers. And the prime numbers I've circled at the end, you always get 4 threes and 2 fives. So 2025, the prime power factorization is 3 to the fourth times 5 squared. And that means we could actually figure out every possible divisor. You may not have thought that you're going to see a rainbow this morning, but here's the divisor rainbow for 2025. I've lined them up in numerical order, and each one, there it is, there's one. Each one matches with its complement, and the product of each pair is 2025. And since 2025 happens to be an odd number, 45 is matched with itself, and it has an odd number of divisors. Um, but a better structure, a better picture for divisors is the Hasse diagram. Um, there's the 5 direction and the 3 direction. And if you start at 1, you can either multiply by 3 up to 4 times, or by 5 up to 2 times. And so every single divisor of 2025 fits into this Hasse diagram. If you move up, you're moving to a multiple. If you go down, you're getting a divisor. is actually called a partial order of the divisors of 2025, partially ordered by divisibility. And if you look at this and think about rotating it around, maybe reflecting it, you actually get a multiplication table. Here's the multiplication table. There's the prime factors, the powers of three and the powers of five. And each box has, each of the 15 boxes has a divisor of 2025. Um, I want to know what the sum is. I know there's 15, but what's the sum? Well, it's a multiplication table again, so I can use the area model. Um, Here's the picture to scale. I'm asking how many little squares are there in this picture, but it's easier to see this way. And the sum of the divisors is just going to be the area of this rectangle, which is 1 plus 5 plus 25 down the left, and the sum of the powers of 3 up to 81 on the right, on the top. So 31 by 121. Way over 3,000 is the sum of the divisors. And I just want to pull off 2025 itself. Um, there's proper divisors, and 2025 is not a proper divisor. And when we add up divisors, we're usually adding up the proper divisors. So the sum of the proper divisors is 1,726. And that number tells you whether 2025 is deficient, perfect, or abundant. If you actually get the sum of the proper divisors being the same as the number you started with, you have a perfect number. If it's more, it's abundant. In this case, the sum of the proper divisors is less than 2025, so we're looking at a deficient number. Um, yeah, okay. Um, Last question. The last question is, in a 9 by 9 grid, I'm going to use the grid lines to make rectangles. Here's three rectangles for an example. I set those up like a Baromean ring. But how many rectangles are there that can fit into the grid of a 9 by 9 grid? Okay, get ready. Counting, type your answers. Oh, this is a tough one. No answers so far. Dare you make a guess? Do you remember the name of the talk? It's 2025. Um, there's a combinatorics way to solve this. If you want to define a rectangle, you have to have a top level and a bottom level, and there's 10 levels to choose from. So you just need to choose two from 10 levels, choose two for the top and bottom, and then the left and right, there's 10 grid lines to choose. Choose two from 10, and so we end up with 10 choose two times 10 choose two. There's the formula for the combination numbers. If I write out the factorial, here's what it is. There's a lot of cancellation. I end up with 45 squared, which is 2025. So this picture, there's exactly 2025 rectangles hidden in that grid line. And that is the end of the talk. Quick talk about the number 2025. I hope it's a great year for you and not at all deficient. Um, and I've actually have a special surprise. Take a look at my new email address. I actually have figured out how to get an upstatenymath.org email, and I'll tell everyone about it soon. Let's see. I'm going to stop recording.